Hello, this is Ali, and today I'm going to talk about model evaluation and fine-tuning. For model evaluation, we either use some loss functions during the model training or use some metrics at the end of uh, training. So metrics are used for model evaluation. An example of metric and a loss function is mean squared error for regression models. In this case, the lower the better, so we have less error. In classification, in which we have categorical outputs, we can use precision recall, confusion matrix, or accuracy, or the average recall in general. In the case of binary classification, we can use ROC curves and calculate the area under the ROC curve. And also we can use calibration plots and Breyer scores. If you want to evaluate your model, you need to make sure that you do it properly. So the proper way and a conventional way to perform training and evaluating is to split your data set into three sets. So first, shuffle over your data and split it into three sets. One set is for training, which is around 70 to 90% of your data, and it contains most of your data sets and is used to build a model. And another part is the validation set, which we use to tune the hyperparameters. These are the parameters that are used to make sure that your model behaves better. Sometimes these hyperparameters are the parameters that your model uses and does not learn during the training. This is 5% to 10% of your trained data. This is part of the trained data. This is the data that is given to you. So the test data is always the unseen data, and it's used to evaluate the final model. You should never use the test set to evaluate your model before the training is finished. When you perform the training, there are some phenomena that could happen. One is underfitting and another is overfitting. So in underfitting, what happens is that you haven't trained your model good enough, or your model is not trained well enough, and there is a large error on the training data. So the reason might be the model is too simple, for example, linear models, or the features are not suitable. You may need to choose other features. Another example is another phenomenon that could happen is overfitting. So in overfitting, you have a very good prediction on the training data, but you have weak prediction on the test data. The reason might be that the model is too complex. So you can see here that like in underfitting, we don't have a perfect fit for the training examples. A good fit is a line that here goes through all the examples. And overfit is trying to match all those sample lines, which is kind of not that great, because you can see in the beginning at the end, like that match causes the model to behave quite irrationally. If you have a lot of features with a small number of examples, also this could happen. So we want to avoid both of these. To help create better models, we use regularization. So it helps us to build simpler models that helps with overfitting. There are a few ways to regularize your model. There is L1 and L2 regularization, early stopping, dropout, and batch normalization is used in deep learning. So L1 regularization and L2 regularizations are the two commonly used regularization types in linear models. So what we do is that we add a term to the objective function as a penalty, and the value of term, when the value of term is high, then the model is complex. So imagine if you look at these two graphs or functions here, you can see that the green function has a perfect match, and it goes over all the different like points that we have. And the blue function goes over the points, but is a complex model. So both of these functions, they have a zero loss on those points, but blue is is overfit here, and the green is a better fit. So auto-regularization actually makes the model choose simpler weights to go for the green function over the blue one. In L1 regularization for linear regression, what we do is that we add a term C and the distance of W, where this is like this is calculated, this term is calculated as the sum of the absolute value of all the weights of all the features. So, and C is a constant. So if you remember, this is the objective function of the linear regression. And now what we do, we add this term here, and now we're looking for the minimum of the objective function plus that term. So when we minimize everything together, it minimizes the size of the weights as well. So this norm will be minimized, and then you have better weights. This is also known as the lasso regression model, and the larger values of the hyperparameter C results in the smaller weights because we're actually adding more penalty. Another regularization is known as L2 regularization, which is quite similar. We add a term here, but the term that we add here is actually the square root of the absolute value of the weights. This is known as the ridge regression, and these two are performing a little bit differently, and both of them enable you to create regularized functions. Sometimes these, like overfitting, underfitting, is talked about as bias variance trade-off. So regularization reduces the variance of the weights, right? Because it adds the penalty. So if the variance of the weights is a lot, too much, then it tries to control them. The less accurate the training, it also means that the model has more bias. It's biased towards specific things, and it hasn't fit the model very well. So finding this balance is a little bit challenging, and sometimes they refer to underfit models as a model with low variance and high bias. So low variance because the weights are the variance of the weights are low, and it has a high bias because it's not fit enough. And overfit models, they have a high variance. You could see the variance of the weights here is quite high, and we have a low bias. Because it's a perfect fit for the training data. So another option that we have for regularization is early stopping. So in iterative learning processes like neural networks, that you repeat the learning cycle multiple times, then you can choose to stop the training before the training error is converged to a minimum amount. You actually use that based on the validation set. So the validation set is similar to the test set because your model is not trained on it, but you have access to it, and you could use it to tune the hyperparameters. So use the validation set to stop the training when the validation set error increases. So when the test error at some point during your training, the training error continues to be decreasing, but the test error, and in which case validation error, could start to increase. So you could try to stop the training when the validation error starts to increase. So now let's talk about a concept called like the confusion matrix, which is used to evaluate classification algorithms. So let's start with the with what we are going to use to create the confusion matrix. So remember that we have some actual outputs, the actual Y, which contains the positive and the negative cases. So this is one class, this is another class, this is the class with output 1, this is with output 0, default, no default, I don't know, like it could be man, woman, like rainy, sunny. So there are different things that we could have here. So a confusion matrix starts to like it works for binary classification, and can be extended to multi-class classification as well. So first, what we need is the number of each actual sample class from your data set. So how many actual positive cases you had, and how many actual negative cases you had. So you have to find these values. Then we try to find the predicted outcome of our model, which is the estimate Y's. So the model could predict some of the samples as positives or negative. So these are these two numbers that we're going to gather is the number of each predicted sample class from your machine learning model. So these two values, like the positive cases, negative cases, they could be the same as predicted. The predicted could be same as the actual, or they could be different. So you agree that the total number of positive cases and the total number of negative cases, the actual ones, might be different from the total predicted negative cases and total predicted positive cases. But the total number of samples are going to be the same. So we just want, in a confusion matrix, we want to know what is actually happening and how many of the actual positive cases were correctly predicted as positive, and how many of actual negative cases were correctly predicted as negative cases. Of course, we have some positive cases, actual positive cases, that incorrectly were predicted as negative cases. And the same way with the like negative cases that were incorrectly predicted as positive cases. All of these, they will add up to create the total predictive positives, total predicted negatives, and of course you already have your total actual positives and total actual negative cases. So now we try to see whether our model prediction was actually true or false. So we name those true positive predictions as true positive, and we call the negative cases that were correctly identified as negative as true negative cases. If there was an actual, if we predicted a negative case as, if we predicted a negative case as positive, for example here, if we had a negative case, but we predicted it as positive, it was a false positive. It wasn't actually a positive, it was actually a negative case. And if we had a positive case and we incorrectly predicted that it is actually a negative case, then it's a false negative. So we call these true positive, false positive, and true negatives. And we use this to create some metrics. An example of a confusion matrix is a spam prediction, an email spam prediction. So the actual number, there are some actual spams, and then there are some actual non-spams. So in a perfect model, the true positive and true negatives should contain the majority of the cases, and there should be the total number of predicted cases. So here we could see that out of the maybe 24 actual spams, 23 were predicted as a spam, and one of them were predicted as not a spam, which is a false negative. And from the total not a spams, from the actual ones, most of them, 500, from the total of this, which is 556 plus 12, that's going to be 568. From the 568 actual not spams, 556 of them were correctly identified as not a spam, and 12 of them were incorrectly identified as spams. So this is where you have a legitimate email, and it will go into your spam folder where it wasn't actually a spam. So what we have is that we're going to have some metrics that are created over the there are some metrics that are created over the confusion matrix. So one of the two of the most important ones are the true positive rate and the false positive rate. So this is basically the true positives over the total actual positives, which should be ideally 1, and this other one is the false positives over the total actually negative ones. So this should be ideally 0, so we shouldn't make any mistakes, and everything should be in the true positive one. And this is something, these two metrics are used further to, we'll talk about that shortly. There are some other metrics, you may have heard about them, like precision. Precision is how many true positives you have over the total predicted positives. So how precise were you in your positives in terms of identifying the true positives? And recall is the true positives over the total actual positives. So it's true positives over the total actual positives. It's just how many of the actual positives does your model recall? How many of them actually remembers? And precision is how precise is it in its prediction in finding the true positives. The accuracy is also defined as the total correct predictions, which is the TP plus TN, the true positives and true negatives. These two are the total is the correct predictions over the whole total number of samples, which is the combination of all other terms. Sometimes we do not have the balanced data set. So if you've got imbalanced data sets, for example, we have in 1,000 cases, we have 900 cases of a positive sample and 100 samples of the negative one. In that case, accuracy may not be the best measure. You could use balanced accuracy. So in balanced accuracy, we just separate these two terms and get the average of them too. And this is going to be kind of the average recall of each class, positive and negative. So balanced accuracy is used when you have an imbalance in your data set. So all in all, we talked about all these different metrics. There are many more. F measure, like their geometric mean. I encourage you to go online and learn about them. So the TPR and FPR that we talked about, the true positive rate and false positive rates, they are functions of the threshold value. So remember in logistic regression, these two, like the output of the model is actually probability, and we could find a threshold. The value of the threshold was actually going to help us determine which of the classes are a positive case, which of the classes are a negative case. So if the threshold is set to 0, it means all the observations are classified as positive. And then if the threshold here you see goes to 0, then both the TPR and FPR rate will be 1. If the threshold is set to 1, then all the observations are classified as negative, and the TPR and FPR is going to be 0. We want a threshold to actually get a very high TPR and low FPR. We don't want them to be both high and low, so it should be somewhere in the middle. So a perfect model is has a false positive rate of 0, so no false predictions, and all true predictions. The rate is 1. So if you're looking for a good model, then we could plot the false positive rate across the true positive rate. And the ideal point in this model in this plot is here. So the false positive rate is 0 and the true positive rate is 1. So we can plot this, and this plot is receiver operating characteristic curve. And if we calculate, another measure that we can find is calculating the area under this curve. So the more this curve is towards that point, the area is higher, and then it's going to be a better model. In parametric models, in which we can set a different threshold and get different kinds of get this graph or different graphs based on different thresholds. Multiple RC curves could exist, and we could change the best one. So now we can extend that to extend our confusion matrix to more classes. So these more classes like could be more than 2. So similar to what we had before, we can put the actual classes, actual predictions, and predicted output here. So class 1, class 2. And then here, if the class 1 is predicted as class 1 and class 2 is predicted as class 2, that's the correct prediction. Everything else is incorrect. So when we have n different classes, then the confusion matrix will look like this. So if class 1 is predicted correctly, we've got it here. And if class 1 is actually predicted as anything else, then it's going to be a false classification. So what we can do here on this, the confusion matrix for multiple classes, is that we could find out which classes are actually predicted incorrectly, and we could fix some of the problems in our models better. The balance accuracy is defined here as the average recall of all classes, which is similar to what we had before, and precision is also as the average precision over all classes. An example of a confusion matrix that you could just create using all these lines of codes. These lines of codes here uses scikit-learn scikit-plot, and just it loads a data set, creates a random forest classifier, creates some and like cross-validation model, and then it creates the confusion matrix for you. And it's a normalized confusion matrix, and you can see the ideal classifier predicts everything here, and this is on the diagonal rows and actually columns of this matrix. You could see that we have the maximum amount of predictions and correct predictions. Everything here is incorrectly predicted, and this is to a total of 1. So this is a normalized one. There are some actual numbers, but this is the normalized one, and this is a digits, like 10 digits classification. So we have 10 classes from 0 to 9. So finally, in hyperparameter tuning, we want to make sure that the learning algorithm actually uses the best hyperparameters. So the learning algorithm works on the parameters itself, but it does not optimize the hyperparameters. So the data scientist is responsible to do that. One way is to use grid search, which is quite expensive, and it could only work for smaller models. Another one is random search, which you could search through the space. Bayesian hyperparameter optimization, heuristic searches like genetic algorithm, and some other machine learning algorithm could model that you create on your own could help you to tune the hyperparameters. In grid search, for example, we search for the optimal set of hyperparameters, and what we do is that we create for each different set of values for each parameter, we go through a kind of a for loop, we create some sets, and that we train the model based on that hyperparameter. Then we choose the set P1, P2, P3, or any more that maximize the metrics. For example, SVM has 2 hyperparameters, C and a kernel, which is an RBF or linear kernel. So for C, the value C, we could set different ranges, and like we have chosen 7 ranges here, and we just want to find out which one is the best. Then for all these 7, we combine that with 2 options that we have for the kernel, and then in total we have 14 sets of hyperparameters. So the first value with linear, the first value with RBF, the second value, and so on. So we train it on these 14 different times and assess the performance on the validation set to choose the best set. And finally, we want to, one of our best friends is the k-fold cross-validation. So in k-fold cross-validation, we want to get the average error of all the folds for a more robust error estimate. Because if we set the test set aside at the end, it's going to be difficult to know whether how our model could have performed on the test set as a training data, and how it could perform on some of the training data as the test set. So what we do is that we choose the test set as a different set of the model each time, and the k-fold cross-validation can be done for these hyperparameters. So the algorithm is quite simple. We split the training data into k-fold, and for each of those folds, we train on all the folds but the k-fold, and we test on the fold k. So we do that, and then we get the average of all the cases. So here is an example of that. So if you have any questions, let me know, and you could comment below and ask me. Thank you.